Did you know that the vibrant colors in gemstones and paints are often due to inorganic compounds? Inorganic chemistry holds the secrets behind nature's palette and the technology that shapes our lives. Welcome to our journey into a realm of atoms and bonds, a world of structure and reactivity that is as essential as it is fascinating. Today, we explore the fundamentals of inorganic chemistry, a subject that not only teaches high school students the basics of science, but also evolves into a powerful tool for innovation in medicine, agriculture, and technology. Inorganic chemistry is the branch of chemistry that focuses on compounds not typically associated with carbon-hydrogen bonds. It lays the groundwork for understanding minerals, metals, and countless non-organic substances that surround us daily. This discipline is built upon the periodic table, chemical bonding, oxidation states, and coordination compounds, all of which come together to explain the behavior of matter. Despite its daunting name, inorganic chemistry is both approachable and deeply relevant. Our challenge has been a lack of clear insight, but today we dispel the mystery through engaging explanations and vivid examples. Let us begin with the periodic table, the cornerstone of all chemical knowledge. The periodic table organizes elements into groups and periods based on shared properties. Each element's position tells a story about its electron configuration and reactivity. This visual roadmap is not just a tool for memorization. It unleashes the power to predict chemical behavior. In this structured arrangement, transition metals such as iron, copper, and nickel play starring roles. Their unique properties, including high melting points and electrical conductivity, reveal the dynamic interplay between atomic structure and macroscopic function. Visual animations illustrate how these metals conduct electricity and resist heat, linking atomic traits to industrial applications. Chemical bonding further clarifies how atoms connect to form stable compounds. Bonds are nature's glue, binding atoms into molecules and minerals. There are different types of bonding, such as ionic, covalent, and metallic bonds, each influencing a compound's properties. Ionic bonds form between positively and negatively charged ions, while covalent bonds involve shared electron pairs. In metallic bonds, electrons flow freely through a lattice of atoms, imparting conductivity and strength. These fundamental interatomic attractions are crucial for building more complex structures. Simple animations highlight electrons moving between atoms, emphasizing the delicate balance of forces that keep compounds intact. Oxidation states are at the heart of many chemical reactions. They indicate how electrons are distributed in a compound and predict how substances behave during chemical transformations. Each element can exhibit multiple oxidation states, which influence its reactivity and interactions with other elements. Through careful control of oxidation states, chemists manipulate compounds to achieve desired reactions. Our graphics illustrate oxidation state changes, reinforcing how shifts in electron count are vital for catalytic processes and energy transfer. These nuances reveal chemistry's hidden dialogue, where electrons are both messengers and mediators in every reaction. Coordination compounds represent another fascinating segment of inorganic chemistry. These complexes form when a central metal atom bonds with surrounding ligands, creating structures that are both elegant and functionally significant. Coordination complexes are not mere laboratory curiosities. They play roles in biological systems and industrial applications. One notable example is the use of cisplatin, a platinum-based coordination complex that revolutionized cancer treatment by interfering with cancer cell DNA replication. Animations showcase the coordination sphere as ligands encircle their metal center, illustrating how these arrangements facilitate reactions such as catalysis and oxygen transport in biological tissues. As one expert succinctly stated, these compounds are vital in both natural and engineered processes, bridging the gap between molecular architecture and real-world impact. Now let us connect these chemical principles to everyday life. In agriculture, inorganic compounds act as essential resources that sustain global food production. Fertilizers containing ammonium nitrate provide critical nutrients that boost crop yields and sustain healthy growth. Superphosphate, another inorganic compound, works diligently to enhance soil fertility, ensuring that plants receive the minerals they require. These applications make the invisible world of atoms palpably important in our everyday lives. Educational diagrams depict how nutrients travel from soil to plant roots, fostering an appreciation for the subtle science that supports agriculture. In the realm of technology, inorganic chemistry is the unsung hero powering innovation. Silicon dioxide is a foundational component in semiconductor manufacturing, making it indispensable to computers and smartphones alike. As we marvel at the capabilities of modern devices, we must recognize the inorganic compounds at their core. Our visuals trace the journey of silicon, from raw material to a critical part of microchips, underscoring the seamless interaction between fundamental chemistry and advanced technology. The marvel of semiconductors reminds us that the tiniest particles often carry the greatest potential, bridging science and everyday utility. Environmental applications further enrich the tapestry of inorganic chemistry. Metal-based catalysts, such as those incorporating platinum and palladium, are used in automotive catalytic converters. These converters reduce harmful emissions by transforming toxic gases into less dangerous substances, making cities healthier places to live. Detailed animations reveal the step-by-step process of oxidation and reduction in these catalysts, providing clear insights into how chemistry can safeguard our environment. The effectiveness of catalytic converters exemplifies inorganic chemistry's promise in addressing pressing global challenges. The intersection of nanotechnology and inorganic chemistry marks yet another cutting-edge frontier. In agriculture, nanoparticles optimize nutrient delivery and improve pest control. They also contribute to soil remediation, creating more sustainable farming practices. These tiny structures, often invisible to the naked eye, offer extraordinary benefits through their controlled reactivity and precise application. Close-up visualizations help students grasp the scale and impact of nanotechnology, shining a light on new opportunities for innovation in the farming sector. Our exploration of inorganic chemistry not only underscores its scientific essence, but also illuminates its practical importance. High school students, who might initially feel overwhelmed by complex diagrams and abstract formulas, now see the subject come alive. The periodic table transforms into a living chart of possibilities, where each element contributes uniquely to the symphony of chemical reactions. Chemical bonds become the narratives that unite disparate atoms into functional molecules. Oxidation states shift like gears in a well-oiled machine, and coordination complexes reveal the artistry of molecular design. Every concept connects to tangible outcomes in technology, medicine, agriculture, and environmental science. Ever wondered how your smartphone functions? Inorganic chemistry plays a key role in its components, and every lesson brings you closer to understanding the science behind everyday devices. Visual aids and animated sequences reinforce learning, while practical examples reveal how the concepts are applied in the real world. From enhancing crop yields with fertilizers to enabling life-saving cancer treatments with chemotherapy drugs, the principles of inorganic chemistry resonate across diverse fields. The subject is not simply academic. It is a vibrant, dynamic force that drives progress in modern society. Throughout this journey, we have addressed the initial conflict, the widespread misunderstanding of inorganic chemistry and its real-life implications. By dissecting its core components, periodic arrangements, bonding types, oxidation states, and coordination compounds, we have untangled complex ideas and made them accessible. Each segment has built upon the previous, ensuring a steady progression toward clarity and comprehension. What once seemed abstract now emerges as a coherent narrative that empowers students to see the relevance of science in their daily experiences. We conclude our lesson by reflecting on the transformative nature of inorganic chemistry. The discipline serves as a bridge between theoretical knowledge and actionable innovation. It teaches us to think critically about the materials that form the world, from the metals in our electronics to the compounds that nurture our crops. In this synthesis of science and real-world application, inorganic chemistry becomes more than a subject. It becomes a lens through which we observe, understand, and improve our environment. Let this lesson inspire you to delve deeper into the captivating realm of inorganic chemistry. Embrace curiosity as you connect scientific theory with everyday reality. Allow the periodic table, chemical bonding, oxidation states, and coordination complexes to illuminate new pathways to knowledge. Every atom has a role, every bond a story, and every reaction a purpose. Today, you hold the key to unlocking innovations that drive progress across industries and impact lives globally. As we wrap up our enlightening exploration, remember that understanding inorganic chemistry grants you the power to decipher the natural and technological world around you. The fundamentals we shared today form the foundation for countless discoveries and practical applications. Whether in medicine, agriculture, or technology, inorganic compounds are the unsung heroes behind many modern advancements. Let your newfound knowledge transform your view of chemistry, sparking a relentless passion for learning and inquiry. Explore the fascinating world of inorganic chemistry and discover how it shapes the technology and medicine we rely on every day.